So we're very happy to have Camille Combe from University of Paris, and she will be talking about Hochschild lattices, a geometric and combinatorial approach.
Thank you, and thanks for the invitation. Today I will present you the Hochschild lattice. So this is another way to study the Hochschild polynomial, and I will present two results on this lattice. So first of all, the Hochschild lattices have been introduced by Frédéric Chapotin. He found these lattices in a surprising way. Indeed, by studying a new order on a combinatorial object called Dyck path, and this new order is called the Dexter order. He found that the Hochschild lattices in a specific interval of this order. So just to give an idea also about the Dexter order, it's an order on Dyck path which is linked to another polytop called the diagonal of the associated one, and used in algebraic topology. So we have something very similar in the way to process. So, and why we call it the Hochschild lattices? It's because the S diagram of this poset is actually the one skeleton of the Hochschild polytop, also called Triwords, if you prefer. Triwords, yes. The Triwords, which appear in topology as a combinatorial model for free loop space, and can be obtained in several ways. For instance, we can obtain this polytop by sequences of truncation. And here, in the combinatorial way, it's another way to obtain this polytop, to see it in another point of view, if you want.
Oh, Camille, I understood your question now. We call it freehedra.
Okay.
Yeah.
So freehedra. Okay.
Yeah.
It's
exactly.
a strange word because it's English and.
Right, I noticed. Yeah, freehedra.
Yeah, it's clear. Okay, freehedra. So I will start by explain what is the Dexter order and what is defined on a Dyck path, and what is a Dyck path also. And I will recall a bijection introduced by Chapotin between the Dyck path of this specific interval, so the Hochschild poset, and a set of words called Triwords satisfying some condition. And I will give two results. I will explain two results, geometric and combinatorial, on this lattice. So the first one will be about this construction, how to obtain the Hochschild poset from lower order. And the second result, it's about obtain a way to enumerate the K-chain of this lattice. So we will see that we obtain this kind of formula where P is a polynomial to define. So it's almost a closed formula, but not exactly. But it's already strange to have this kind of form of formula for K-chain. I have not other example of posets when we have this kind of formula. So this is quite surprising. And I will finish this talk. By giving other property, because here I will explain only two properties. So there is obviously other property, combinatorial and geometric. And we conclude by giving new results obtained by Henri Muhl on this lattice, and give open question. Okay, so in algebraic combinatorics, we like to study combinatorial objects. Okay? For instance, permutation or tree. And some of these combinatorial objects have the property to be enumerated by the Catalan number. So this is the formula here. For example, one has binary trees, no crossing partition, Dyck path, triangulation, etc. And what we want to do on this family of combinatorial objects is to find a way to compare to order this object via partial order. So sometimes we can define a partial order very naturally with the set of combinatorial objects that we study. This is the case, for instance, for the ternary order on binary tree, where the covering relation is given by rotation move. So here I draw what we call an as diagram, and I draw the smaller element at the top of the diagram and the greater element at the bottom. So you can see this diagram as an oriented diagram, an oriented graph from the top to the bottom. And here, this is a binary tree of size 3, because we have 3 internal nodes. You can see also the rotation move as the non-associative relation. For instance, if you see a binary tree as the bracketing of k elements, where k is the number of leaves, so here 4 leaves, so we have 4 elements, and simply the rotation move is to move the brackets from to the right. Sorry, we move to the right the brackets for the non-associative relation. Okay, and there is other way to obtain an equivalent order, but not in the same set of objects. For instance, we can define the ternary order on Dyck path. This is very equivalent, where this time in this object we define what we call sorry, a sliding move to obtain the covering relation. So by covering relation, I mean just the direct relation between 2 elements. We passed from this one to this one, and from this one to just as a direct relation between the elements. And also we can change the partial order and not change the set of elements that we are looking at. This is the case for the Stanley order on Dyck path, for instance, where this is an inclusion on Dyck path. We give the partial order. So what we have to understand here is that there is many ways to define partial order on a set of combinatorial objects. So in Dyck path, there is many order, and the Dexter order is a new order on this object. And if you want to understand what is the Dexter order, I have to explain what is a Dyck path first, finally. So a Dyck path is simply a path with up step and down step that we can denote by 1 and 0 for the down step. This is a path in a positive quarter plane where we have to start at the origin here, and we have to we want to have the same number of up step and down step. So we always hand here. We start here, we hand here. So I need to give more vocabulary about Dyck path. First of all, a Dyck path is said to be primitive if we cannot obtain this Dyck path by concatenating two non-trivial Dyck paths. This is not the case of this example. This is not a primitive element because we can, for instance, here concatene this path with this one here. So this is not primitive. And we say that X is a subpath. So for a factor, X is a subpath if X is also a Dyck path. So for instance, here it's a subpath. Here it's another subpath. And we say that a subpath X is movable if it is primitive and it can be expressed, our Dyck path D can be expressed with X here, with this kind of expression where P and S are a prefix and a suffix, and where we have two conditions on S. Either S is a trivial path, or he has to start by an up step. So if I take the big example here, we have only two movable subpaths. So we have this one here and this one here. You can see when I yeah, I think that's okay. See, I take the smaller example here. We have two movable subpath 2, this one and this one. So this is the same Dyck path. In this example,
I have a quick question. What does the notation 1, 0 to the m mean?
Oh, it's 1, 0, m. The power m means that we have to repeat m times 0.
Okay, I see.
Where m have to be strictly positive.
Okay, I see.
Okay. So what is meant is that you have to have a number of 0 of down step here before you move up subpath. Sorry, here you have to have this down step, this down step. Okay. And when we have movable subpath, we can describe the covering relation of the Dexter order. So to define the Dexter order, it's easier to define the covering relation of this order, and finally to define the Dexter order as a reflective and transitive closure of the covering relation that we denote with a point here. And this covering relation is simply that when we take a Dyck path with a movable subpath X, you can move this X, for instance, for this one, you can move this subpath here, sorry. Either you can move it from just 1, 0. So it's make this x here, this subpath here, and this give this Dyck path here. Or you can move it to 2 dump step. So just here, and you get this left Dyck path here. And for this one, you have only one possibility because you have just one dump step just before your movable subpath. So you have just one way to increase this element. It give this Dyck path here, and this is this combination give us all the Dexter order. So if you want to draw the as diagram for size 3, because we have 3 upstate, so this is dimension 3, order 3, sorry. We obtain this kind of poset. And on the right, I draw the Tamari order to compare the two. The Tamari order on the set of Dyck path of size 3, 2, just to see the difference between the two. So in the Dexter order, what we can notice is that we don't have a lattice because we have several maximal elements. We have this one and this one, which is not the case for the Tamari lattice, which is a lattice, because all elements can be have a meet and a join, or if you prefer, an infimum and a maximum. Supremum, sorry, an infimum and a supremum for each pair of elements which are comparable. And this is not the case for the Dexter order, so this is not a lattice. This is a meet semi-lattice, in fact. But this is another story. So now that we have defined the Dexter order, we want to look at this particular interval in this order, and the first Hochschild poset will be here. Just spoil alert! It will be these 2 elements here for this side. So what we want to look at is a particular interval in this order, this Dexter order, between the Dyck path 1, 1, starting by 1, 1, 0, 0, and following by 0, 1, 0, repeat n time. So 1, 0, 1, 0, 1, 0, etc. And the greater element of this interval is given by this Dyck path, starting by 1, 1, repeat n time, 0, repeat n time, and ending by 1, 0, 0. So the Dyck path of this interval have several property, satisfy several property. The first one is that all the Dyck path in this interval have to start with 1, 1. We cannot have something else for this interval, and have only value of height 0 or 1. So a value is simply, if I take here, is simply a dump step following by a up step. So 0, 1, it's a value. And the height of the value is simply this height here. So for instance, this value have a height 0, and this one have a height of 1. Hey, I'm not sure about the pronunciation, sorry. Another property is that the sequence of height of the value is weakly decreasing from the left to the right. What we can see here, we not really in this example, but maybe in the bigger example after. And the first property is that all the paths of this interval have to end either with 0, 1, 0 or 0, 1, 0, 0. This is a fact shown by Frédéric Chapoton about this interval. And this is this interval, not R, denote E, that we call the Hochschild posets, the Hochschild posets. And as I say in the introduction, the as diagram of the Hochschild poset is the one skeleton of the Hochschild polytope, or free Edouard. So here a bigger example of the Dexter order, and the particular interval, the Hochschild poset, is here, where the smaller element is here, and the greater, is here. Okay, but we have defined this particular interval, and this is the Hochschild polytope. This is Hochschild poset, which is the one skeleton of the free Edouard. But it's not really nice to work with this kind of object. First of all, the description here of this interval is not really easy to avoid, not really easy to play with. And the Dexter order is not very simple too. If I give you two Dyck paths, how can you say easily if there is or not in this particular interval? How can you say if one is smaller and greater than another just by looking at and not by doing all the process to be sure that that works? So what we want to do now is to find a way to encode this Dyck path in an easier object, combinatorial object, and such that we have an easier faster order on this new object, easier than the Dexter order. And this is given by what we call Triwords. So a Triword is simply a word on the alphabet 0, 1, 2, such that the first letter has to be 0 or 1, cannot be 2. And if we have 0, a letter equals 0, then all letter or following letter have to be different from 1. So we will not have 0 following by 1 and the size of a Triword, it's simply the number of the letter of this word. So here I give the first, the three first set of Triword size by size. So for size 1, 2, and 3. And this is our candidate, the set of Triword, to encode the Dyck path of this interval that we see. So first thing that we see about Triword is that the number the cardinality of Triword is given by this formula here. And this formula I will talk about later in the case of enumeration of cation, because it's a particular case for the two shade. Now we have easier objects, and that come with partial order very naturally, which is given by the component-wise order. So the component-wise order, very simple as the partial order, because we say that for two triwords, U and V, U is smaller than V if for each letter of U, we have that U is smaller or equal to the letter V for the same position. And the set of triwords on the way with this partial order is a lattice. Indeed, for each pair of elements, comparable elements, we can define the join and the meet operation, meaning there is a infimum and supremum element for each pair of elements. So now we have on one hand we have the triword with the component-wise order, and in the other hand we have the Dyck path with the Dexter order, and we want to establish an isomorphism of poset between the two. Isomorphism of poset, meaning that if two Dyck paths are comparable for the Dexter order in the Hochschild poset, if and only if the two triwords corresponding have to be comparable for the component-wise order. So it's a if and only if condition here. So this bijection is described in the paper of Chapoton, and I will try to explain it on this example, how to go from this Dyck path to this triword. Sorry. We have to read from the left to the right our Dyck path. So when we see a factor 1, 1, except for the two first letters, we have to add 1 at to a counter denoted by N2. Sorry. And we stop when we see a valley. Sorry. So and start. So the first factor 1, 1 cannot be count. So we start here 1, 1. We have one factor and 1, 1. We have two factor 1, 1. So N2 become 2. Then we see a valley here, and we have to note the height of this valley. So the height of this valley is 1. So we add 1 for our triword, and we have to make 2 letter 2 because of the counter 2 here, saying that we have to repeat N2 times the letter 2. Then then we make our counter N2 back to 0, and we start again. So 1, 1. We have one factor 1, 1 here. So N2 become 1, and we found another valley here of height 1. So we had 1 here, and because we have just see one factor 1, 1 before this valley, we just add 1, 2. Then we're not having factor 1, 1 for the last 2 valleys, so we just add 0 and 0 for the height of this valley and this one. So this is not a very easy bijection between these two kinds of objects, but it's work, and actually it gives us the isomorphism of posets. and allows us to conclude that the component-wise order on Triwords reunites the Hochschild lattices on order n. And here is the first, it's the realization called the cubic realization for the Hochschild lattice for order 2 and 3. So this is a particular realization here because we look the Triwords as real space coordinates. So here, for instance, 0, 0, 0 gives me the origin in 3D, and the greater element is here, 1, 2, 2. So we have here the smaller element and here the greater element, and we always have in from the top to the bottom. And here the comparison, the comparison between two Triwords is very simple because it simply look at letter by letter between two Triwords. So now we start with I will talk about first results about the construction of this poset by the operation of interval doubling. We say also that is a congruence uniform lattice, a lattice which is constructed by interval doubling. It's the same thing. And first, I need to explain what is an interval doubling. So this is an operation on posets, not necessarily a lattice. You can do this in a poset. And when you take a poset, for instance, here I draw this poset P. If we want to doubling one interval, so for instance, this one in black, we have to give a new order inherited by the order of P. So we have to following this four assertion here. Simply, we will see that an element X and Y are comparable for this new order if we have this four assertion satisfied. So in an example, if I have X and Y, which is not in the interval that I want to doubling, for instance, this element and this one, they have to stay, they will be comparable with X smaller than U if at the origin it was the case. Same thing if we take an element X not in the interval that I want to doubling and U in this interval, so for instance this element here, then when we doubling, so in U prime and B, U prime and B, we have to sorry, we have X is smaller than U if it was the case between this element X and U prime. And same thing for the two other assertions. So we have to keep something reasonable for the order, for the original order. So if the poset that we are looking is a lattice, sorry, then the first property that we can say is that the poset obtained by doubling an interval is still a lattice. So the lattice property is keep it for this operation, for this doubling operation. And we say that a lattice is constructed by interval doubling if this lattice is isomorphic to a poset obtained by performing a sequence of interval doubling from the singleton lattice. So the singleton lattice is simply two element related, simply this poset here. And here I draw the first poset that we obtain with all doubling operation. So if we start by the singleton lattice here, we have, for instance, two choices. Either we doubling this element or this one, and we obtain this poset here. Okay, just you have to doubling this one, for instance. You obtain this poset, or you can choose to doubling all the posets, all the singleton posets, and we obtain this square here. So you can notice that here we have the pentagon, which is the as diagram for Tamari order, but also for Hochschild poset for the first dimension. And here we have all the hypercube. So on the right, I give a counterexample of a lattice which is not constructible by interval doubling. Why? Because here we have 5 elements, and if it was possible to obtain this lattices by a doubling operation, we will necessarily see this lattice in this diagram, because here, except for this one, we have already element lattice with 5 or plus elements, 5, 6, 5, and 6. And from this one, it's not possible to obtain this lattice. So this lattice cannot be obtained this way. Okay, so what we want to do is to show that Hochschild lattice can be obtained by doubling operation. And actually, we will show that we can obtain the Hochschild lattices of order n+1 from the Hochschild lattice of order n only by 2 steps plus 1 which is cosmetic. So we see 3 steps. So the first step is to give a copy of the Hochschild poset of size of lower size n, simply by adding a 0 at the end of all triwords. So this is something that we always can do because they're not in contradiction with the definition of triword. We can always adding a 0 at the end of a triword. So we make a copy of the Hochschild poset of size n. The second step is to consider the union of T0 with T2, where T2 is simply another copy of T0, where we replaced the last letter of all triwords ending by 0 of T0, so necessarily ending by 0, by 2. So this is our first doubling, if you want. We're just doubling all the posets, the subposet T0 with T2, and we consider the union of the two posets. The the first step, yes, a little more complicated. It's just to take the union of T0 and T2 and T2, sorry, and adding a copy of an interval of T0 called I0, which is all Triwords of this form. So starting by 1, then having 1 or 2 as letter, repeat a number of times, and ending by 0. And simply I1 is the set of element of I0, where we replace the 0, the ending 0, by 1. And this first step allows us to show that finally the Hochschild poset is constructible by interval doubling. So here an example of this doubling operation. The first step is simply adding 0 at all the Triwords of the Hochschild poset of size 2, because here we have Triwords of size 2. We add only 0 here everywhere. Then we doubling all these subposets simply by changing all the 0 by the letter 2 here. And the last step is simply doubling this interval in T0, so 1, 1, 0 and 1, 2, 0 by changing the last letter 0 by 1, and we obtain 1, 1, 1 and 1, 2, 1. And we can see that we obtain the Hochschild lattice of size 3. So there is several consequences of the fact that this is lattices constructed by interval doubling. First, we can deduce that this is a direct consequences. This is what we call a semi-distributive lattice, which means that we have these two implications that being satisfied, where the V is the symbol for the join operation, and the other symbol is for the meet operation. And the second consequences is that since we just have to make two doubling operation between the Hochschild poset of size n-1 and to obtain the Hochschild poset of size n, we only need two doubling operation. We can conclude that to obtain the Hochschild poset of size n from the singleton lattice, we need two n-1 doubling operation.
Camille, can I ask a question?
Yeah.
Can you obtain the one skeleton of associahedra from interval doubling?
Yes, because this is the summary lattice. The one skeleton of the associahedra is given by the summary order.
I see.
So here is the first the first one, and yes, you can show that this lattices is also constructible by interval doubling.
And how about permutahedra? Do you know?
Okay.
Maybe not, right? Because you don't see here the.
Yeah, no, I think I think it's possible for this one. I have a doubt. I think combinatorial, yes, you can. So I would check. I think yes.
Okay.
Okay, so in fact, this number of interval doubling that you need to obtain your poset from the singleton lattice, it's also the number of journey reductive and the number of meteor reductive. So this is element which have only one covering element, or that be covering by only one element if you want to see the geometric thing. So there is this kind of correspondence. Okay, so I will talk quickly.
Actually, let me just say something. The two-dimensional permutahedra has 6 vertices, right?
Yeah.
So, but was that in the picture here?
No.
Oh no. So
no, but can we obtain it by?
Okay, we can talk about it later.
Maybe with the. I wonder if you just doubling this element here, you can obtain the hexagon.
I see.
I think, yeah.
Okay. Yeah.
But not this one.
Question? Yeah, can I ask a question? So how did you get from the this tree? So I should have paid better attention, but since we're discussing this, so if I go down the tree, so you have the one vertex, the two vertex graph, then the square, and then the pentagon. So how do you get from the square to the pentagon? You insert the interval at the left vertex.
It just this element here that you have to doubling. To obtain this pentagon.
And doubling means you.
So you can doubling this one too for obtain the hexagon. Yeah.
Right. That's right, because then that would be the same thing, just to double that. So you don't have to. But so I wasn't sure. So doubling. Oh, you can double any subgraph or something. Yeah, I have to read your slides. It wasn't clear to me what the doubling actually does.
Any interval.
Yeah. Any interval you can double. Okay.
Yeah, and one element, one vertex is also an interval.
Right. Yeah.
Because you can have a repeat
square. Okay, and then. Right. Okay. Yeah. I'll figure it out. So okay, then because then you have this one. So yeah. Right. So you have one, and then you could make these longer. Okay. Great. So you can chain. Yeah, that's interesting. And did you say? Are you going to say this? Yeah, I shouldn't interrupt you because you're running out of time. But you mentioned truncation. So there's a way to get the simplices, to get the pentagon, and so the permutahedra and sort of the isosahedra from a simplex by truncation using hypergraphs, sort of in completion of hypergraphs. So Jovana Obradović, she's probably some predecessor. At one point, she was in Paris. To just give a very nice talk about this. Is this somehow related, or?
I know. I don't know. I'm not sure about that. Yeah.
Okay, never mind.
So I will try to end this talk quickly by talking about the enumeration of cache of this poset. So simply what we want to do is to obtain the enumeration of tuple, of k tuple, all comparable 1 to 1, 2 by 2, such that we have the first reward smaller than the second, smaller, etc. for the component-wise order. We will represent this cache this way. So you can have repeat of reward in the cache, of course. This is the same thing as interval. The two chains are the interval in the poset, and the one chain are the elements in the poset. Okay. So to obtain an enumeration of this cache, a way to do that, a way that I found, it was to classify all this cation depending of the presence or not of letter 0. So for instance, here the set denoted by ZI is the set of all cation having I Triword in this question without 0. So for instance, here for Z2, we have a 5-chain gamma, which have no 0 for the last 2 elements. For the last 2 Triword, we don't have 0. So this is what it belongs to Z2. And the 5 is because we have Triword of size 5, and the other 5 is because this is a 5-chain. Okay, so another example of 5-chain, this time of size where we have a Triword of size 4, and here we have I equal 3 because we have 3 elements, 3 Triword without 0. So when we have this classification, we want to know about the cardinality of all elements, and for that we have to make how I say we want to find a way to obtain the set of cation of size n via the set of cation of size n-1. And we found that with this application here. So I will explain this application with an example. For instance, if we look at this gamma, this 5-chain here, to build gamma prime, sorry. So the cation of size with element of size inferior, we have to forget the last letter in gamma. So here we have to forget this 0, this 0, this 0, this 1, and this 2. And this is gamma prime. And we have to notice what is the number of words in gamma ending by the letter 2. So in gamma, the only Triword ending by 2 is this one. So we note T equal 1. And to rewrite gamma from gamma prime and T, simply we have to see that here we have I equal 3 because we have 3 elements without 0, and gamma belongs to Z2. So necessarily the element here we're missing, that we miss to rebuild gamma was 0 because we want to pass from 3 to 2. Okay. But now, what is the element missing here and here? Is it 1, 1 or 2, 2 or 1, 2? This is this parameter T who says that who allows us to know what is the solution. So because we have T equal 1, we know that there is only one element ending by 2 in gamma. So necessarily, this is this element ending by 2, and by elimination, this one ending by 1. So this bisection between this set and this set here allows us to describe the cardinality of all the sets of cation ZI, sorry. So we obtain this formula for each cardinal cardinality, sorry, of each set of cation, depending on the parameter n, k, and I, of course. So, for instance, if we look at this set Z1, 2, 3, we have all this cation here. We have all this friction here, and we can, because of that, know that the three first elements came from this set. The second two elements, the second two friction, come from this set, and the two last come from this one. And this formula we can rebuild, we can rewrite via triangular matrices. So this is all the description of the cardinality of all the sets Zi. And what we want to say here is that when we want to know the cardinality of all cation, we have simply to consider the sum of all little z I here. So finally, the sum of all this element, of all this cardinality of the set Zi, give us this formula. Unfortunately, this is not a closure formula, closed formula, because here we just have, we know that P is a monic polynomial of the group K, but I don't have a formula to describe P in all situations. So we have to compute for each K what is P. But this is already surprising to find this, this factor here, which is present in all cases. So if I give an example of that, for instance, for the number of intervals, meaning for the two shell, we obtain, after computation of this matrix, we obtain that the sum of the little z give this formula. And here is a polynomial that we want to describe. So if we go further for the case 1, 2, 3, 4, 5, and we can go after, we obtain this kind of formula. So here, for the case of one chain, we obtain the number of elements of the Hochschild lattices that I give in the beginning. For the number of intervals, we obtain this one, etc. for the second limit. And another surprising thing is that when we look at the constant element of all polynomials, so 370, 142, we obtain a sequential number already known as the number of connected functions given here. So these constant terms are already new, and I don't know why. I think we don't know why, but me, I don't know why. And another thing very interesting is that this is not a property in only the Hochschild lattices, because we can also look at subposets of the Hochschild posets. Sorry. For instance, if we restrict a Triword of 4 Triwords starting by 1, we obtain what we call mini Hochschild. Why not? By keeping only this space of this poset. And here, what is funny is that when we want to compute also the Cation of this subposet, we obtain something very similar, from the Hochschild posets. And here are the first equation that we obtain for the enumeration of Cation for the mini Hochschild. And here the constant elements 1, 2, 6, 24 are the factorial number, and we don't know why always. So the mini Hochschild is also interesting because it seems to share many properties of the Hochschild poset. I don't know if there is a way to use in topology area of this mini Hochschild, but in combinatorics it seems to have a beautiful property too. Okay, so I will finish by simply give you other results that I show in my article. So with the citation for the notion here for all this notion. I will not, yeah, please. And I will also end by talk about new results on this Hochschild lattice obtained by Henri Mill very recently. For instance, he gives a description of the Galois graph of this lattice. He also shows that the coordinal order of this lattice, which is a normal way to ordering elements, meaning Triwords in this lattice, is isomorphic to a certain shuffle lattice already known, introduced by Green, etc. And other line of investigation, I talk about mini Hochschild. A way to continue this investigation will be to obtain over generalization, like mini Hochschild. What is the over restriction? We give something interesting on the Triwords element, for instance. Another line can be found with op algebra. Why not? Because we have Triwords elements. We want to define a co-project and project. It's very tentative. I'm not sure about the word. Sorry. And the last point, it's about a recent result, which is a generalization of the fundamental theorem of finite distributive lattice. So here it's for semi-distributive lattice, which can be worked for our case here. And we stop here. Sorry for the time.
Thank you. So let's thank Camille.
Thank you. I hope it was enough clear, because my accent, my English accent is awful.
It was good. Are there any questions or comments?
I just have a quick question. So why is it called Hochschild lattice?
The what? Sorry.
Why is the lattice called Hochschild lattice?
I don't understand the word.
So anyway,
Why?
It's the guy's name. I think you say Hochschild or something.
Yeah.
Yeah. So it's German. It's Hochschild. But in any case, why is the name? So is that related to his work or somehow, or you define these posets? But what significance do they have?
For the mini Hochschild?
No, just the regular one even.
Yeah. Why I define? I'm not sure to understand the question. Why I define the Hochschild?
I think he's asking for the name. Why is it called Hochschild?
because
Right.
just because it's the Hochschild polytope, because it's one skeleton of this polytope, just for that.
Yeah, Ralph,
The
I think I can explain in terms of
Yeah.
your perspective. So you can construct a model for the free loop space of a simplicial set by taking kind of like maybe I'm going to call it co-Hochschild chains on the chains coalgebra on your simplicial set, right? And then this chain complex is isomorphic to the chains on certain cellular complex. And the cells in this cellular complex are certain polytopes that are associated to Hochschild monomials. And these polytopes can be characterized, and they were called by Samson Sanablidze Hochschild polytopes.
Okay.
You know, like in the Kovar construction story for the base loop space, we have cubes. Naturally,
Right.
we have cubes. And in this Hochschild case, you in the same idea naturally produces this Hochschild polytopes.
Okay. And then, but it's not like, but you did ask to the relation for the permutahedra. Are they related somehow?
Yes. So that's a kind of a different story. If you take cubical chains on a cubical set,
Yeah.
and you take Hochschild on the coalgebra of cubical chains,
Okay.
the natural cells that appear in this model are permutahedron.
Because you would expect those from Milgram's model. I mean, if you
From what?
Milgram's model for the loop space, just geometrically.
Oh, I see. Yeah. Yeah, this should be closely related, actually. Yeah.
That's why I'm asking, and then
Yeah.
we say, are they sort of Schwappeltal has this nice result that you can get the associahedra as a blowdown of the sorry, actually Agni Tong says that result that you can get the associahedra as a blowdown of the permutahedra. You were asking the inverse question, right? And can I blow up the pentagon into the hexagon? So that's so I was wondering if there's some sort of explicit blowdown or blow up of these Hochschild things that I can sort of understand what the point is.
I see. Yeah. There should be an inverse operation to this interval doubling, maybe.
Yeah, contraction.
Contraction.
Yeah, that's right. And sometimes it's easier to show that something is constructible by interval doubling by showing that you can contract your poset to obtain the singleton.
And did you say that somehow so you do this doubling? Are there sort of some maximal elements in there? So what I'm asking is like, are how do cubes and permutahedra sit in there? It's like you have this tree of doublings or whatever it seems to be. And is there some order on that tree? You drew it, yeah. So
yeah, well, the order on this tree is it's an interesting question. Can we consider this as a poset too?
Right, something like that. Yes.
Yeah, and see if there is an easy order on it. I don't know. I think about that, but not very.
So right, I mean, so the question is, you have the left branch, which just gives you linear trees. That seems to be whatever it is, minimal. Right. And then my question was, if there was such an order, would the permutahedra be maximal?
I don't think it would be maximal from this picture because it would lie in the one before the last branch, right? But it's interesting because it seems like cubes, associahedra, and permutahedra lie in the same branch.
Right.
right? Like in the same path, right? Like in the
Right. Yeah, but you'd have to go see the cube is sort of simpler because you can already get it in this row, but you have to get to the permutahedra. You have to have one more row. So in the sense that, you know, and it's still planar, right? The cube already exploded into a dimension higher, while the permutahedron you would get by blowing up the associahedron, which is still of a dimension lower. These are just questions because I'm sort of interested. And the other things, I mean, they sort of don't count, right? Because they have tails. So
Right.
the two kites don't count because they have tails.
Yeah. So I'm interested in all this because I've been modeling loop spaces, free loop spaces. And there are these,
I know nothing about it, sorry.
yeah.
You can explain.
But this is useful to make computations for the homology of the free loop space and things like that. It gives me tools to label, to count, and so on. Yeah.
Okay.
Maybe I have one more quick question. So what is it? So you mentioned the semi-distributive laws. So what do you do with them? Well, every time I have a combinatorial, I ask stupid questions. Because I mean, this sort of the join operation. So it's just very, very much to the end. You had some consequence which was said that something has a semi-distributive law.
So what I do with
That one, yeah, right.
Semi-distributive, I heard.
Right. So what do I get from that?
From the fact that this is a semi-distributive lattice.
Right. Yeah. What do I in general? What do I get from having a semi-distributive lattice?
So, for instance, the last point that I give, you obtain a way to keep the investigation of your lattice if it checks this property. For instance, for the fundamental theorem for finite semi-distributive lattice. Not sure about if my reference is.
No, I mean there is something like there's this Ehrenborg-Hopf algebra, which sort of goes also back to Roda, so it's called Ehrenborg-Hopf algebra. And then I think this is just something about joins and something like that. That's why I'm asking. It's for you can generalize it for polytopes. So there's like a polytope Hopf algebra, which generalizes the incidence Hopf algebra. So you can start with an incidence Hopf algebra, and then you can generalize it to a polytope Hopf algebra. And I think, you know, there's similar things that you're using. That's the kind of question. And then the other type of question is if you have something like that, usually, you know, this is a discrete version of something like a Lie bracket. Like a Poisson bracket. So yeah, in the Poisson bracket, you have a multiplication and a bracket, and then you have the Poisson identity, and this is something like this if you would put sums in, so you have to linearize it.
Okay.
This is somehow, that's some structure I came across that always is also interesting. And
interesting.
it's very similar, right? I mean, it's like if you take A, B, right, I mean, you take the terms, you take a bracket A, B, C, and you take A out to the left. And then, so this sounds similar to that, where you take A out to the right and something like that. But anyway.
Okay.
I'm wondering if it sort of has some algebraic. So if it's a discrete version of something algebraic, so if you would apply a chain functor to the polytopes, you would get a sum.
I think yes, but yes, I think. Not sure. Sorry.
All right, I have to go. So thanks very much for the talk.
Okay, thank you for the question. And sorry for not not giving a satisfying answer.
No, these are open-ended questions. I mean, I just ask random questions. Sometimes you get an answer, sometimes you don't. But it's it's just a discussion. There are no. So most of the questions I have don't have definite answers. They're just think about. All right, thanks. So see you.
Are there any other questions? Not, let's thank Camille again.